Good afternoon. Let's get started. So this is the Cloud Native Buildpacks session, the deep dive. We did an intro on Tuesday, and in this talk we're gonna kind of dig more into the meat and bones of Cloud Native Buildpacks. I'm Terence Lee. I go by Hone02 on Twitter. I work at Heroku, and I co-created the Heroku Buildpacks API. This is my colleague Joe Kutner, goes by Codefinger on Twitter and not GitHub, I guess. But he also works at Heroku. He's a architect on the languages team and is in charge of the Java experience on the platform. So with Heroku, Heroku is often considered like the first modern day PaaS that's out there. Today we run over 7 million applications and process over 23 billion requests a day. And over 8 years ago, we launched a technology called Buildpacks. And Buildpacks allowed us to basically become a polyglot platform, so allowed us to run more languages than Ruby, which was kind of the only language we supported initially when we started. And Buildpacks are a modular, opinionated way to take source code and turn them into runnable applications for Heroku. And what that means is that we look at the language configuration in your application and can use that to prepare your application for production. And since then, we have open sourced the technology back in 2012, and that allowed other people to extend the platform as well as other people to just adopt this technology inside of their own build pipelines. Since then, the next evolution of Buildpacks is this project called Cloud Native Buildpacks. So it's why you're here today. And it has contributions from both Heroku and Pivotal, which are the two largest Buildpack platforms out there today in production. And in October, it got accepted as a Cloud Native Sandbox project. So we have a vendor-neutral home to kind of move this project forward. And so at a very high level, what a Cloud Native Buildpack is, it takes your app source code, you run it through Cloud Native Buildpacks, and you end up with a Docker or OCI compliant image. And with that image, you have layers that map logically to your application, and we're going to go into details what we mean by that. So today, first off, we're just going to run through what it looks like to actually just like take an off-the-shelf build pack, run it through a Cloud Native build pack, and how that all works and how you can get a running Docker image and use that. After that, we'll take a look at how you actually build a Cloud Native build pack, and then we'll take a look at how you combine different build packs together into a kind of build pipeline that works with your application if you need to kind of do various things as part of the build process. And then finally, we'll show how you can kind of deploy this stuff.
Okay. Can you hear me? Okay. So the first step in running a Cloud Native build pack is getting the tooling that you need to do so. So you can do that with the Pack CLI. This is a tool or a project that's part of the buildpacks.io project on GitHub. So you can go to the releases page on GitHub and download the binary for your platform. We have them for Linux, Mac, and Windows. Okay, so that's the only prerequisite, and with that installed, we'll head over to the terminal. So I'm going to take a pre-written Java build pack. It's one that I wrote and maintain, and we're going to run it on a Java application. So the first thing I'll need is a Java application. So we'll take the Heroku Java Getting Started app, which is a very simple Spring Boot application, hosts a web app. It exposes some REST endpoints, connects to a database, real standard stuff. It has a POM XML, so it's a Maven project and all the basic structure of a Maven application. So to build this with a Cloud Native build pack, I'm going to run the pack build command. I'm going to generate an image called myapp, and I'm going to do this with the Heroku Buildpacks builder image. So this Heroku Buildpacks builder image contains not only the Java build pack, but all the Heroku supported Cloud Native build packs, as well as the tooling required to run those build packs. So this is what pack is going to use to execute my Java build pack. So when I run that, the first thing I'll see is that it detects that I have a Java application. It did that because it saw my Maven files. So it starts running the Java Buildpack. It installs the JVM, it installs Maven, then it runs Maven to compile my code and download my dependencies. So the first time Maven runs, it's going to download all my jar files from Maven Central, but it will cache those, so subsequent runs will be faster. Now the way it caches these is by putting them in a sort of a special layer that it can reuse, but that won't go into the production image. And in that way, I can make changes to my application or to the layers below my application without invalidating that cache. That's actually something that's impossible to do with Dockerfile. Okay, so my Maven build is complete. The last step in the build pack was that it detected that I'm using Spring Boot. It looked at my dependencies, and so for that reason, it knows what command to use to start my application. So it outputs some metadata with the java-jar command that the platform should use to run this application. And then you'll see it emits a few layers. So it's going to export the output of the build pack into an image. So we have a layer from the Java build pack for the JDK. So it contains the Java binaries, a layer for my app, and a layer for some configuration. Okay, so the result is the my app image, and that's a Docker image just like any other Docker image, so I can run it with Docker run. I'll publish port 5000, and then you'll see just a regular Spring Boot app starting up, binds to a port, and I can go about running it. So this is great. I can generate a Docker image without having to change my application or add any code to my application. But the benefit of build packs really picks up when we get to day two operations. So when I need to do things like update my JDK or rebase or update my operating system, build packs have some key advantages. So this Java app is using Java 8, and the build pack by default just installs the latest version, the latest security version of Java 8. So I'm just defining that I want 1.8. But maybe I want to pin to a very specific update version, so I can modify this system properties file, which is in my application, to say that I want update 192. So then when I run the pack build command again with my Heroku Buildpacks builder image, I'll see that it detects Java, but this time it's going to install update 192, and then it's going to run Maven, but it'll use that Maven cache, which is still valid because it should not be invalidated by a minor JDK update, and then it emits the metadata and exports a new version of my image. Likewise, if I want to update or apply security updates to the operating system, I can actually do that without rebuilding those layers at all. So there's the pack rebase command, which is part of the pack CLI. So I can rebase my application, and I'll add no pull because I haven't pushed my app up to Docker Hub. When I run this command, it's going to reapply those application layers, the app layer, my JDK layer, and my config layer, on top of an updated version of my base image. So to sort of illustrate this, the original image we created was based on Ubuntu 18.04, and I had a JDK layer, an app layer, and whatever other layers might have come from my build packs. And then when I run the rebase command, it takes that newer version, that security update of 18.04, and sort of lifts and shifts those layers on top of it to create a new image. But it does not rebuild those layers. So when it comes time to publish my image, the layers for the JDK and the app are already in my repository. So when I go to push the image, those don't need to be transferred. And in fact, the update version of Ubuntu might already be in that repository because one of my coworkers or somebody else has put it there. So if it's the first time, only that layer will be transferred. But it's very possible that a rebase operation, when being published, doesn't require the transferring of any layers. Okay, so we were able to do all of this without a Docker file. We created a Java-based Docker image. We were able to cache our dependencies in a way that we can't do with Dockerfile. We can keep that cache when we're updating things like the JVM. We can also customize the Maven build. So even though build packs are opinionated and sort of have defaults for how they expect things to work, you can still customize them to make them work the way you need to. You can also customize the JDK if you need to add certificate bundles. And then finally, and most important, you can compose that Java build pack with other build packs to create this build pipeline to perform other jobs. For example, you might add Node.js to prepare your JavaScript assets for production.
So I think Joe showed that these build packs are kind of these like generally reusable components, similar to, I guess, like the closest analogy I can think of with Docker images that people use today are stuff on the official like images from Docker Hub. But the difference is that unlike that, generally for Buildpacks, you don't have to pull them down and then extend those images to make them work with your application. Kind of out of the box, all the things that Joe talked about are things that you can use straight with the Buildpack without having to modify the Buildpack at all. So as an example, the Heroku Ruby Buildpack that we have out there in Heroku has been in production for 7-8 years, and it's used by millions of applications. And most of our customers never have to touch or use it, and they just get to use it day to day without having to worry about what work goes into that Buildpack, which is really nice. And kind of with that, since these things are these like independent, cohesive units, you can actually combine them together. So if we want to use multiple Buildpacks, like Joe was talking about using Java and Node, but in this case we might use like Java, Python, and potentially Ruby, maybe not. So the first thing we need to do is actually determine if we should run these Buildpacks. And so there's this detect process. So in the example Joe was talking about, we looked for like the POM file to see if it's a Java app. And then for Python, like we want to check if it looks like a Python app. And for Ruby, we would do the same thing for Ruby, right? And in this case, we detect that it is a Python and Java app, but not a Ruby app. And with that, we have information of what we need to do to actually build the application. So with that information, we know the Buildpacks we need to run and then what order we need to run them in. And then we can actually go and build the application. And so at the end of it, you get a set of directories that get turned into layers. And so the Java Buildpack produces a Java Buildpack folder, and the Python Buildpack produces a Python Buildpack folder as well. And so each of these map into, so I was talking about how the Docker image is made up of logical layers that represent your application, and this is what I mean by that. So, we talked about with just the Java-specific case that there was that JDK layer, and then also that dependency layer, and then the application layer. And so we're able to map these folders into actual layers into the Docker image. And so when you're doing kind of multiple Buildpacks together, there's just additional layers that get added for the other Buildpacks as well. So there would be a Python runtime layer if we run the Python Buildpack, and this dependency layer might actually be made of multiple layers where you would have the Java-specific stuff that's coming from the Java Buildpack and the Java folder, and then the Python-specific stuff from the Python one, and then you have your app code configuration, and then all that stuff sits on top of the base image. And with that, we can go look at how we actually, if we wanted to combine these things together, how we actually create a Python Buildpack from scratch.
Yeah, so there are many reusable, off-the-shelf commodity Buildpacks, and for most Buildpack users, those are sufficient. But there are times where you want to create your own Buildpack for some specific purpose or because you have some particular need. So that's what we're going to walk through here. We're going to create a Buildpack for Python. So to do that, we need to understand the Buildpack API. The Buildpack API is a formal specification that's part of our Cloud Native Sandbox project. It's a work in progress, but it defines the entry points and how Buildpacks run. It's also a vendor-neutral specification, so it's got contributions from the community. So you can find that on GitHub. But at a very simple level, the Buildpack API has 2 entry points. There are 2 executable files, bin detect and bin build. These can be written in Bash or Python, or in the case of the Java Buildpack, they're binaries that are written in Golang and then compiled down. The language you choose is completely your choice. So we're going to build our Python Buildpack in Bash. It's a great lowest common denominator. Most people understand it, and it's actually very good at doing some of the things we need to do, like mutating the file system, setting up the environment for other processes to run. But you could also choose to write a Python Buildpack in Python if you preferred. Okay, so the first step in creating the Buildpack is making a directory for it to live in, and then we're going to create the bin directory under that and touch our 2 entry point scripts and make them executable. Then we're going to open them up in Vim, and we'll start with our bin detect script. Paste in our shebang. Bin detect. So bin detect's purpose is to determine if the given application source code applies to this Buildpack. So it takes as input the application source code, which comes from the current working directory, the environment variables, and some metadata about the build. As output, it produces an exit code, either non-zero if this build pack does not apply, or 0 if it does apply. So you can see up here in my usage comment, the detect script has 2 arguments. The platform directory, which contains serialized environment variables, which you can choose to export or not. These are done this way because you might have environment variables that you don't want to have exported in the context of your build. For example, in the Java build pack, you might have Java options that are meant for to configure your garbage collection and heap size in production, but you don't want those to apply to your Maven process. The build plan is some of the metadata that comes from the build execution process. And then the other input is the application source code, which is the current working directory. So what I need to do to run detection is look in this directory to see if I find files that represent a Python application. And the one file that I'll look for is a requirements.txt. This is a file that Python apps use to manage their dependencies. So if I do not detect that file, I will exit non-zero. And if we do find that file, I'll just echo the name of my build pack. So that's the entire bin detect script. Most bin detect scripts are this simple. Some are even just exit 0 no matter what. But a few will look at certain environment variables to see if a particular service has been provisioned and things like that. Okay, so we're ready to move on to bin build. We'll paste in our shebang. So bin build at a very high level takes 4 inputs. The application code, just like bin detect did, and the environment variables and metadata, just like bin detect. But it also takes in layers. These are layers from previous build packs in the pipeline. So if a build pack before me was the Node.js build pack, it might install a Node.js runtime that I can use and execute. The purpose of bin build is to prepare your source code for runtime. So in the case of a Java application, it's going to compile into bytecode. For Python, it's going to download our dependencies and install our server and things like that. The output of bin build, in addition to the prepared code, are layers. So we'll have a layer for the JDK or the runtime that we're installing, or maybe our dependencies. Along with this, some metadata that the build pack execution environment can use, for example, to know what process or what command to start our application process. So our goal here is to create a set of directories like this. We're going to have our build pack directory, which is our layers directory, where we're going to create a layer directory for Python and a layer directory for our dependencies. Our application will have a directory, and then we're going to have some metadata called launch toml. All of these will be assembled by the execution environment into my image. Okay, so the first step, you can see I have 3 arguments here. The layers directory, those are my previous layers. It's also where I'm going to write my new layers. The platform directory and the build plan are the same as with bin detect. And then my current working directory is the application source code. So my first step is just to set some variables for the appdir and the layers.dir just to make them easier to reference. The next step is to set up my environment. So I'm going to pin to a specific version of Python 3.6.7. A more advanced build pack might inspect the application code and see what version this app needs. I'm also going to pin to a specific version of pip. Pip is the package manager for Python. And then finally, I'm going to set the URL for a precompiled Python binary that I'm going to install. Now, I could also build Python from source in this step, but it wouldn't really demonstrate anything special about build packs. So I'm just going to do the more simple installation of a precompiled binary. But if we were to look at the official Docker file, or the Docker file for the official Python image on Docker Hub, there's a 34-line run command that compiles Python from source. And we could pretty much just copy and paste this into our build pack if we wanted to, and that would work. But we could probably get rid of all the ampersands and line break stuff like that and use functions and make it testable. We have a lot more power within build packs because we can actually use higher level languages. Okay, so my next step is to actually install Python. So I want this Python to go into its own layer. So I'm going to create a new directory within my layers directory called Python. And then I'm going to download from that URL, so curl from that URL, and then explode it with tar into my Python layer. If something goes wrong there, I'll just exit 1 with a message. That'll terminate the execution of this build pack. If it's successful, I'll put the Python bin directory on my path so that I can use it in subsequent stages. And then the last thing I'll do is write my metadata. So each layer comes with a TOML file of the same name. So I'm going to write this TOML file to tell the execution environment that I want this layer to be present at launch. So this is a runtime layer that I want to go into my production image. I also want it to be cached so that the next time I run my build pack, it will be available. I won't have to reinstall it if I don't want to. And along with that, I'll add some metadata, like the version of Python. So on a subsequent run of this build pack, I can analyze that or inspect that version and determine if the Python version has changed. Then I'll reinstall a new one, or I might skip the install altogether. All right, the next step, step 4, is to install pip. Again, pip is the package manager for Python. I'll do that by downloading the get pip script from pipa.io and then just running it with the Python runtime that I just installed. And it'll install that specific version of pip for me. After that, I need to run pip, which will prepare my dependencies. It'll install the dependencies for my application. I could just run pip straight out, and it would install them in the global environment. That means it would put them into my Python layer, because that's where my site packages is. But what that means is that if my dependencies change, when I'm transferring layers and deploying new versions of my app, I also have to transfer the Python runtime itself. So I'm going to split my pip dependencies out into their own layer so that if they change, I can deal with them separately. So I'm going to create a new pip layer directory and then a couple directories under that, an env directory and a modules directory, because I need to create some environment variables and I need to put the modules in their own place. Then I'm going to run pip install with my requirements txt. I'll tell it the target directory is my modules directory under the pip layer. I'm going to add the install option so I get my bin scripts. So when I run commands like gunicorn, they're going to be on my path. And then just a couple other options that are helpful when running pip. After that, I need an environment variable at runtime. So the env directory within the layer is special. So we adhere to like the POSIX standard. So if we see a bin directory within the layer, we'll put it on the path automatically. And if we see a file within the env directory, we'll set that as an environment variable at runtime. So I need to put that modules directory on my Python path so that they'll be available in production. And then finally, I'm going to write a pip layer TOML file. I just want this layer to be present at runtime, and I won't cache it. The last step is to write metadata, and this is optional. So this is where we can add special information about our app from the build pack. And in this case, I want to try and tell the execution environment what command to use to run the application. So I know that if this is using gunicorn or gunicorn, I know what command will be used to start the app. So I'm going to just grep the requirements txt to see if gunicorn is being used. If it is, then I'll grep around the Python scripts to see what Python script is calling the getwizgy application. If I find that script, I'll convert it to a module name. And then I'm going to write my metadata file, my launch TOML. This is sort of a reserved file within the layers directory. This is where I can write process information. And I'll create a new process type called web. And I'll tell the execution environment that I want it to run gunicorn, the name of the module, bind to 000, and then log to standard out. Obviously, if I wanted to create a more robust build pack, I could take this step, which is a little hard to read, and put it into its own tool, maybe a small sharp tool that I just execute from bash. But this is it. That's my entire build pack. So with about a little less than 70 lines of code, I've created a build pack that's reusable, that can be applied to just about any or many Python applications. There's one more file I need, though. It's a descriptor. Uh-oh. We'll see how that goes. OK, I need a buildpack TOML file. That's this one right here. This is a descriptor that tells the buildpack run environment about my build pack. So I need an ID that's universally or globally unique. I'll call it Kutner Python. I set a version. I need a name that's human readable. And then I need to define what stacks my build pack works on. And I'll say it works on Heroku 18. So a stack in the context of a build pack is a construct that actually represents two images. a build image and a runtime image. The build image will contain GCC and headers that I need to compile things, and then the runtime image won't have those. It'll be slimmed down to have a smaller, surface attack or security surface area. So we're just going to make this work with the Heroku 18 stack, which is just the Heroku packaging of Ubuntu 18.04. Okay, so our build pack's complete. We want to run it, and to do that, we need a Python application. So we're going to clone the Heroku Python Getting Started app. It's a really simple Django application, uses Gunicorn. It has a requirements txt and just a fairly standard Python application. So we're going to run the pack build command to generate an image called my app. We're going to use the Heroku Buildpacks builder again, but that Heroku Buildpacks builder does not contain the build pack that we just wrote. So we're going to pass the build pack flag with the path to our build pack directory where we created this build pack locally. When we do that, pack build will ingest that build pack into the builder image and run it on our application. So when we run that, we'll see that immediately it detects that we have a Python application. It saw our requirements txt. It'll install Python. It'll install pip. It'll then run pip to download and install our dependencies. And finally, it will generate the metadata and export an image. So now this image has a layer for Python, a layer for pip, a layer for the app, and a layer for the config. So a couple extra layers. But the end result is my app image, which we can again run just like any other Docker image. We'll publish port 8000. And there's the Gunicorn command that was the default command emitted by the build pack metadata. Okay, so now let's take that Python build pack that we just wrote and let's combine it. Let's compose it with the Java build pack that we ran earlier. A use case for this is like a machine learning application that's primarily written in Python but needs Java for something specific, or maybe a Python app that needs Java to parse XML or interface with Kafka, something like that. So the first step in doing this is we need a new builder image. So that Heroku Buildpacks builder image won't work for us anymore. So the first thing we're going to do is write a builder.toml file. This is a descriptor that describes what Buildpacks our new builder image is going to contain. We're going to use the Heroku Java build pack that we ran earlier, and this is the URL where it gets downloaded from GitHub releases. We're then going to add the Kutner Python that we just wrote, and we'll use the path to that directory that we put it in. Below that we have our build pack groups. This defines the order of execution and requirements for those build packs. So we have the Java build pack is optional. So if that build pack does not detect a POM XML, the execution environment will continue on. We won't just stop dead. But the Python build pack is not optional. So if we don't find that requirements txt, the whole thing will break down. Okay, so then we're going to run the pack create builder command, and we're going to create a builder image called Kutner Buildpacks. We'll pass it the builder config, the builder toml, and we'll define this as working on the Heroku 18 stack, just as we did before. And that's going to generate a new Docker image for me that I can use with my pack build command. But before I do that, my Python app is going to need a POM XML in order for the Java build pack to detect it as a Java app. So I'm just going to add a very minimal POM XML here, but you can imagine this is where you might add a dependency on the Kafka client or something like that. So I'll copy this into my Python app, move into that directory, and now I'm going to run pack build again, generate the my app image, but this time I'm going to use that new builder, my Kutner Buildpacks builder image, and I'm going to add no pull because I haven't pushed this to Docker Hub yet. So that's going to run, and the first thing we'll see is that both Java and Python have passed detection. So those two build packs will be executed. First, it'll run Java. It'll install the JDK, run Maven, install Python, install pip, run pip, and then ultimately export an image from those layers. So you can see now we have one layer for our JDK, one layer for pip and our dependencies, one layer for Python, one layer for our app, one layer for the config. And then we can run this image to inspect it and see that we have composed these things. We're going to run just a bash session And if I run Java version, I see there's my Heroku JDK, and if I run Python, I get my REPL. Is this me? Okay. So it's great that we've been able to compose these things. It allows us to create very complex and very useful images. But composition does more than just allow you to combine things. It allows you to extend without modifying. So you can take these off-the-shelf build packs like Java or Python or Node.js to prepare your static assets, but you might also add in special concerns that are specific to your environment, to your organization. Maybe you have an APM, like a New Relic build pack, that cuts across all of your apps, whether they're written in Ruby or Java or Python. It installs an agent that instruments your code and sends metrics up to New Relic. Or maybe you have specific logging concerns within your organization. You have a special logging format, or you need to send logs to Splunk or Logstash or something like that. You can create a logging build pack that combines with these other build packs, rather than forking those build packs and changing them, or like copying and pasting bits of Dockerfile around. I don't think we're going to have time to deploy, but we could take that Docker image that we created and push it up to a registry, and just like any other Docker image. So the main thing to take away from this talk is look at all the things that I did not do. I created a production runtime image, and I didn't have to create a Docker file. I didn't have to go look on the web to find out what order I need to put things in and copy and paste bits until I have a special Snowflake Docker file for my application that I have to make sure doesn't bit rot. I also didn't have to know anything about the Java build pack. I just consumed it. It installed the JVM. It put it on my path, and it's there ready for me to use. I didn't need to know about the structure of the official OpenJDK image or something like that. I didn't need to add special files or twiddle them around as I'm adding my application code into the image to get a better caching behavior or incremental build behavior. I didn't have to dance around user permissions and the fact that I have root access when I'm running a Docker file. I didn't have to force Docker to rebuild layers when I needed to apply a security patch. The pack CLI handles a great deal of that for me. I didn't have to understand or operate the base operating system. That operating system, if you're running on Heroku, is managed by Heroku. If you have your own environment, you might have an operations team that takes care of those security updates, and maybe they're the ones running rebase. And then finally, I didn't have to couple my app to my build pipeline. I didn't have to add a special configuration file that tells the build how it works. My app code is just my app code, and I let the build pack determine how best to prepare it.
So in summary, I think you can break a lot of things that Joe was talking about down to a few kind of categories here. So we talked a bunch about composability, combining the Java and Python build packs together. But I think like the real value is that because these are these independent composable units, we can take these things and kind of combine them together, and then also the ability to just leverage off-the-shelf things together means that it can be very quick to kind of build some of these, your custom build pipeline for your application without having to pull it down, extend it like you would normally with a Docker file. If you have to combine multiple of them, you then have to also deal with like multi-stage Docker, which can get really ugly because it requires you to just understand what is actually in these Docker images that you're trying to do multi-stage builds from. We've seen a bunch of stuff with like how the build pack just understands a lot of things about the language. You can design it in a way where you can do stuff like know to run GUnicorn for Python if it detects it, or just know for Spring Boot applications you can configure it to do that kind of stuff. Detect things from the environment. And in addition, because of those things, we can also have fast as a feature, right? Like we're able to have really quick builds with Java, with Maven, because we can cache specifically the M2 cache for Maven, but not actually export that into our production environment. So we're keeping our image small, but we're also still getting that incremental performance that we normally get when we just run these things locally. So those are the kind of things that we mean when we talk about app-aware and reading that language-specific configuration. And then most importantly, it's like really easy to build this stuff together, but ultimately once you ship this thing in production, it needs to be maintained and live, and that probably takes up way more time than actually just building the application to start with. And so there's a lot of things with like the rebasing that we talked about, like some of the speed of just being able to quickly rebase and not have to deal with even the build time, but also the publishing time of like pushing this stuff to the registry. But then once it's in the registry, when you need to push these images out to the actual server nodes that run these applications, they get to leverage all the same layer efficiencies that we've seen throughout this talk. Because this stuff is decoupled from your actual application, like you're not checking a Docker file in for your application to customize your build pipeline, there's less code that you have to maintain. And then in addition, the operations teams that are actually operating these applications, the amount of surface area because of composability means that there's a much smaller subset of things that they have to vet and review to ensure that like the stuff that is going into production actually complies with various compliance standards that you have for, say, like HIPAA or PCI or things like that. And then because the whole, we aren't mixing as operational concerns as part of the build process as a app developer, it also means that things like we're talking about, like the root access with Dockerfile, like you don't have to set your user when you're running this thing in production to make sure it's an actual user that isn't root, like when you're running it, right? Because you don't necessarily want your application to be running as root when you're actually running it in prod. So these are things that are just handled for you because you don't have to worry about those things with Buildpacks. And it really comes down to, at the end of the day, that Buildpacks are just a higher level abstraction as compared to Dockerfile. So it means that this is built for application developers, and it's at that level. And so it just means that there's just a ton of concerns and other things that you just don't have to focus and worry about, and that we can meet developers where they want to focus on, which is their app source code, and delivering kind of value to your customers, right? Because you can focus on actually delivering features. And this kind of goes back to the container era that we're in these days. I feel like when you're in a container ecosystem and you're developing in a container environment, when you're using stuff like Dockerfile, you don't only have to be an expert in both like building your application and kind of the domain that your application runs in. You also kind of have to be an expert in Docker and Dockerfile. Like you have to understand the concerns, like when that file gets checked in, someone has to maintain it. It doesn't stay clean forever. Like we have Dockerfiles internally at Heroku that we use for development. And I went to go like contribute a code to our API project, and the Dockerfile didn't work. I had to like actually patch it and send a PR because this stuff doesn't just stay working forever. And so you can go and try all these things we talked about today. Try out Buildpacks. There's a Buildpack GitHub repo. And so the formal specifications under the spec repo, Lifecycle is a project that is used by the Pack CLI, and it's part of the stuff that actually runs the actual Buildpacks and images. There's the Pack CLI itself. All this stuff is open source. You can go check it out, fork it, run it, use it. We have a Slack for the community that all of us are in. So Joe and I, as well as all these people in the front row who are also working on the project with us. And so come join us, try out the Buildpacks. Come talk to us in the Slack. And then as well as there's a samples repo under the Buildpack project that just has like all the way stuff from like hello world, kind of like I'm not really doing very much with the Buildpack, just want to kind of go through that process, to a Java and Node Buildpack as well. Cloud Foundry has a handful of Buildpacks, and then the Java Buildpack that we ran through at the beginning of the talk is also open source under Heroku, and Joe has the Python Buildpack that we went through and just built available as well. So if you don't want to go build that Python Buildpack, you can just clone it and then run it and then kind of edit it for your own sake. So that's kind of all we had. We have a bunch of shirts as well, Buildpack shirts that people in this front row are wearing. Please come talk to us, ask questions.
Yeah, I'm taking a flight out tonight, and I don't want to take these shirts with me. So help us.
Thank you.
Slides, there were several locations to try out our Buildpacks. Do you intend to make these all together under buildpacks.io? Because I think I remember I tried out Buildpacks something like 2 months ago, and I had trouble finding out different Buildpacks, actually. So do you have a plan to Because, well, for example, here,
Yeah.
you've got Cloud Heroku, buildpacks.io. I mean, it's kind of spread out. Not
Yeah.
very easy for consumption.
Yeah, so the question, we're going to repeat the question. So the question was, we have all these build packs, like a listener samples. Is there kind of like unified place basically to kind of go and look and find for that stuff? So currently today, for the Cloud Native build packs, we don't have something out there that you can just go and find every single build pack that's there. At Heroku, we published we've released a build pack registry, but that's kind of the older non-cloud native build pack stuff, and it will be updated to kind of take into account all this cloud native build pack stuff. And the plans are to have a registry that will run as part of the CNCF space as part of that in probably the coming year or so.
On to my second question. What do you think about JIT, for example, for maybe for Java developers, because there's an integration for Dockerfiles or whatever, so that covers most of the Java projects, that is native to the programming language, right? JIT is with Java, it's going to do everything, building, pushing, and do a whole shebang within Java. So how do you, well, I don't know if it's a fair question to you, but how do you think you compare with this approach? What do you think about it?
Yeah, so the question was, what do we think about Jib and how do we compare and kind of contrast like Cloud Native build packs to Jib itself? I think Jib, the project is great. Like all this stuff that's come out of Google and all these other places, I think all fall in line with all the things that we're also trying to do in the Cloud Native Build Packs project, which is we don't find that Dockerfile is the right level of abstraction. I think for any application developer that's really kind of doing the day-to-day kind of stuff, that's not to say Dockerfile is bad or wrong. It's just not the right level of abstraction, I think, for application developers. And I think projects like Jib help prove that kind of stuff. And Jib's a great project. I think specifically in comparison to Cloud Native Build Packs, one of the things that is the way we've done it this way is that we want to have a kind of language agnostic way of handling these things, and build packs were a way we've done that for many years, and kind of battle tested in production. And being able to being tied so specifically to Maven would make it hard to kind of share that kind of stuff, like say I want to do this in Go or Python. Ruby or Python or another language, right? And so the fact that, like in this GitHub repo, the fact that we have the specification or life cycle in the pack CLI means that as a build pack, as a person who wants to write build packs to support other languages, I can follow the specification. I can build a thing specific to Java, like Joe has done. I can build a specific thing to Python. I can build a specific thing to Ruby, but still leverage all the other stuff in the kind of build pack ecosystem, which is we can share tooling like the pack CLI to actually go ahead and build that stuff. Whereas if I was to do something like Jib, it would require resources to basically integrate that thing into pip. Or you kind of have to pick what the kind of winning solution, right, is in the ecosystem. So for Python, it's like, do I integrate with pip? Do I integrate with pip-m? Do I, tie this into virtual env? And so it allows us to kind of sidestep a lot of those kind of issues and other things, and really focus on having a more general solution that is easy to plug and then can leverage resources together. I don't know if you had other stuff to add.
No, that's great. And we'll be around. Let's take questions offline now, just so we can free up time.
Yep.
But yeah, we'll hang out for sure.